Here's a short little update on my solar tracker project. I have the housing of the linear actuator off right now. It's not really necessary. I'm just troubleshooting and getting sensors tuned up. Um, Basically, there's 3 wires coming out of the end of the actuator. 2 of them are for DC power, and the third one is a couple sensors that I have mounted at the bottom. This thing has mechanical limits. It can only turn so much to the east and so much to the west. And when it gets to those limits, the motor needs to know how to stop. So I have the microcontroller looking at these magnetic switches. When magnets pass them, it says, okay, you can't go any further. And then beyond that, I have an emergency stop switch, which will just turn the motor off if that fails. And same thing on the top for the upper limit. So as the actuator moves up and down, it has mechanical bounds built into the electronics. There's 2 photo cells up here, which talk to a microcontroller and tell it, where the sun is, where the brightest part of the sky is. And the microcontroller just basically turns on the linear actuator to move the panel into the sun. I don't have any solar panels mounted on here because you don't need it while you're troubleshooting, but I will put it on later. I plan on using this beast. I had everything connected to a solderless breadboard, but I recently soldered and positioned it all down to this control board. Without going into too much detail right now, I'll post all the schematics and the design later. These are 2 relays which change the polarity to the actuator motor to either make it go up or down, and that's controlled by the input from the sensors to the Arduino. The Arduino goes, okay, go up, go down, and it talks to this relay through a couple little coils. But I have a terminal board or terminal strip over here. I basically have, there's 4 terminals, 4 screw terminals that are different on here. These 2 are just input from my 12-volt DC battery power, and that goes to the relays. From the relays, there's a couple different switching setups, but they all go back to these 2 screw terminals over here. And, this can be 5 volts and this could be ground, and then the microcontroller can make it the other way around, so that controls the polarity of the DC motor through these 2 screw terminals. These 2 photo cells up here, I have the programming set so that when this one, the microcontroller reads both of these, and then I have one's called sensor 1 and sensor 2. When sensor 1, it calculates the difference between them. So when sensor 1 the difference is greater than sensor 2, then it'll move this way. And when sensor 2, the difference between 1 and 2 is greater in the negative region, then it moves this way. But basically these two little photoresistors just are sensitive. The resistivity is sensitive to how much sunlight's on them. So that's kind of how I get my directional control. It's very simple, very easy, and it's very accurate. When they manufacture these things, they tend to have different resistances built in. I ordered 7 because I know that they're not very precise when they're manufactured. They are 75,000 ohm photocells when you order them, but when you actually test them at home, you put like a piece of tape over them and test the resistivity to each other. Some of them were up to like 3,500 ohm off of each other, so I found the 2 that are the closest to begin with. But obviously the way that I have it set up, if I really want this thing to aim directly into the sun, I need their values to be almost absolutely perfect. So the way that I got around that is when I come back to my control board, I have the wire right here coming in. I have a voltage divider set up with a potentiometer, a 1K ohm potentiometer. So the 2 photo cells that I got together were very, very close in number. But to be perfect, I have this little trimming pot. I can turn it either way. And that's in series with one of the photo cells to add or subtract, or to add some resistance to one of them, or take it away from that threshold point to make it the exact same resistance of the other one. And that seems to work very, very well. So this other terminal is the input from the Hall effect sensors. But basically I'll show you how it works. I'll turn power onto it. Right now I have the microcontroller powered from the computer, and this is the Arduino software. I have the serial monitor spitting out data to me to let me know what's going on. Basically, it's telling me that it's daytime, it's giving me both sensor values, and it's giving me the difference. It goes very fast until it locks on to the brightest part of the sky. Right now I have the motor off, so the sensors are working, the microcontroller's on, but the motor can't actually turn it, so it's never really achieving the brightest part of the sky. But if I turn the battery power on, right now I don't have anything on it, so it's actuating, and it's finding the brightest part of the sky. It's tilting down towards the eastern direction. It's probably 7 something in the morning. And it's, the brightest part of the sky is in the east right now. So it just found it. When it finds it and it stops, that delay is 3 seconds. I'm actually going to make it a little bit more like 15 minutes because I want it to be as accurate as possible. I have a little flashlight here to simulate the sun. It might not look perfect because this augmented light is just kind of manipulating the natural sunlight, but so we're going to call this brighter over here. The sun's over here. The linear actuator will actuate. It's kind of hard to see, it's going slow, but watch the shadow underneath it. As the shadow creeps to be underneath that bubble, the sensor bubble, you know that it's more perpendicular with the sun. So you can see there that it's right underneath it. If I move it this way, it actuates back the other way to be in the sun. Bam, turns off. So it's going to kick right back on here in a minute. It's very accurate, but because I have it set so accurate, it constantly adjusts the... it'll constantly adjust the position of it. So basically what I'm going to do is that delay, I'm going to make that more like 10 or 15 minutes because the sun tracks across the sky pretty slow. I'll also have to do some testing. And then basically at nighttime, I have something set up. I'll simulate that with a towel, and I put that over the sensors. Hopefully a bird or a butterfly doesn't do this during the day. That basically simulates nighttime, and this thing will tilt back to the eastern sky. This front face is facing south, or it will be, and so that means if it's leaning this way, it's going back towards the east. And a nighttime value will send it back to the east, and then as soon as the values start becoming daytime values, it'll start tracking again, and it'll go back this way. So I'll show you that. You can see it leaning this way back to the eastern sky. And then as the sun comes up, as it is right now, and it's moving this way, it'll track up. This thing has mechanical limits that it can only, go to. These hinges right here only allow the board to come fully extending this way and this way so much. Well, the linear actuator doesn't know that. It just turns the motor on and moves it there. So that's why I have these Hall effect sensors here. I have the 2 Hall effect sensors. This one, which they're operated with magnets. So there's one here and one here. As the actuator comes down, it's going to hit these. There's going to be magnets mounted right here. The magnets will trip the Hall effect sensor, and the Hall effect sensor goes to the microcontroller, says, whoa, the actuator's almost all the way down to the base, turn it off. It doesn't physically cut the power to it, it just turns the relays off. If that was to fail on either end, just beyond the Hall effect sensors, I have a hardwired lever switch which will actually cut the power so that the actuator is like spinning on all threads so it doesn't come down to the output shaft of this motor and just kind of, stall everything and burn up the motor. That's a fail-safe that probably won't ever have to be used if this thing's working correctly, but, with all electronics, you don't expect them to always work correctly, so you build fail-safes. So I also have a, lever switch and a Hall effect sensor at the top as well. So it's basically my project, and that's the update so far. I still need to mount this in the control box, which we're working on, and, it's a slow process because I have to glue some stuff in there. But other than getting the project box mounted, which will go on this side down here, and making a couple more adjustments so I can have seasonal angles on this thing and take it to other parts of the world, potentially wherever I move, and let this thing actuate for different angles of the sun at different latitudes in the earth. So that's the project so far. It's pretty neat, and I'll be posting probably an Instructable to show people all my circuit design and kind of what I did here, so it could be duplicated on the cheap. The actuator that I built here, it's crude, it's homemade, but it works, and it's really strong. I can put a pretty heavy solar panel on here if I get bigger hinges, but comparably for the amount of travel that it's making, I think around a foot it travels in and out to actuate the sun. That's comparably $300+ linear actuator, so I'm pretty proud of my ability to build it with what I've learned at school. So that's basically it.